Welcome to the Explainer. Today, we're diving into a topic that's practically guaranteed to rewire how you think about modern warfare. Listen, for decades, pop culture has completely programmed us to picture laser weapons in a very specific way, right? We expect instant, flashy, explosive blasts tearing through spaceships. Well, today, we're going to completely bust that Hollywood hype. We're strictly looking at the facts, the data, and the gritty, real-world physics of directed energy weapons. Okay, let's dive into this. The absolute fundamental truth we have to start with is this. These are not Star Wars death rays. I know, a little disappointing, but honestly, the reality is actually much more fascinating. Modern militaries have completely moved past the experimental phase here. Systems like the US Navy's Helios, the UK's Dragonfire, and Israel's Iron Beam are real. They are operational or near-operational defense systems being deployed as we speak. We're witnessing a true technological leap. But to really get it, we have to unlearn literally everything the movies taught us.
Section 1. Not science fiction anymore. The paradigm shift. Section 2. How military lasers work.
So how do military lasers actually work? We need to totally shift our focus from that myth of the instant explosive blaster, because the actual mechanics behind this are incredible, and they're rooted entirely in thermal dynamics, not concussive force. Militaries aren't using these to blow up alien motherships. They're deploying them for counter-drone defense, rocket interception, and close-range air defense. A modern military laser is, at its core, a highly advanced heat delivery system. It generates a super concentrated beam of coherent light and focuses it onto a tiny point. It doesn't instantly blow things up. Instead, it transfers intense thermal energy. It literally melts electronics, burns right through structures, and ignites fuel. And to pull that off, it absolutely relies on a crucial concept called dwell time. The beam strictly must stay accurately focused on the exact same spot on a moving target long enough to cause a failure.
Now, what's really interesting about this slide is the sheer engineering complexity required to achieve that perfect dwell time. It's mind-blowing. If you look at the internal components of a ship-mounted system like Helios, you've got these high-capacity generators, pumping out massive electrical power, which is then converted into coherent light inside the laser modules. But check out step 3 in the diagram, the adaptive optics system. This right here is the secret sauce. Before the beam even fires, these deformable mirrors and sensors are actively compensating for atmospheric distortion in real time. They're bending and shifting to make sure that beam stays perfectly focused. Let's actually walk chronologically through how a typical naval engagement plays out over just 1 to 5 seconds. First, the ship's radar detects an incoming threat, say a drone swarm. Second, the combat system locks on, the turret whips around, and those highly advanced optical systems refine the aim. Third, the beam is stabilized against the violent pitching of the ship and the atmosphere. And finally, the target is continuously heated. If that beam holds its dwell time, the drone's motors overheat, its structure totally weakens, and it just drops right out of the sky.
Section 3. The economics of defense. Now, you might be wondering, if engineering this perfectly stable, heat-delivering beam is so incredibly difficult, why are militaries so eager to adopt it? Well, the answer is all about money. It's about the terrifying financial imbalance of modern drone warfare. Just take a look at this stark comparison. In modern conflicts, hostile forces are launching extremely cheap, mass-produced drones. To shoot those down, militaries have historically had to rely on traditional interceptor missiles, like the ones used in the Iron Dome. Now, those missiles are incredibly effective, no doubt, but they carry an exorbitant price tag. We're often talking $50,000 or even hundreds of thousands per single shot. Firing a $50,000 missile to destroy a $500 drone is, frankly, an economic disaster. But a laser shot is powered completely by electricity. $5. That is the extremely aggressive cost per shot number we're looking at for a directed energy weapon. Let that sink in, from $50,000 down to $5 or less. This is exactly how lasers uniquely solve the massive economic problem of defending against cheap drone swarms. It gives the defending military an almost infinite magazine depth. You're literally only constrained by how much diesel you have for your generators.
Section 4. Atmospheric challenges and limits. So if lasers are this cheap and this effective, why aren't they just everywhere by now? Well, enter the ultimate antagonist of our story, physics and the weather. Rain, fog, smoke, dust, humidity, and sea spray, these everyday weather conditions act as massive hurdles. While a laser might have a typical effective range of 1 to 5 kilometers under perfect conditions, you introduce just a little bit of bad weather, and that effectiveness is severely, severely degraded. As you can see right here, this perfectly explains why this happens. On one hand, we've got ideal, clear conditions where the beam delivers high energy straight to the target. But look at the degraded conditions. The atmosphere itself actively fights the weapon. Moisture and gases literally absorb the laser's energy. Particles of dust or smoke cause scattering, physically breaking up the light. The beam just becomes weaker and weaker before it even reaches the drone, meaning your target might actually survive the hit.
And this brilliantly illustrates one of the most frustrating challenges they face: thermal blooming. Get this, even on a perfectly clear day, the sheer intense power of the laser heats the air it's passing through. This superheated air causes refractive index variations that actually distort and defocus the beam itself. It is exactly like that wavy, shimmering effect you see hovering over a hot asphalt road in the middle of summer. The laser is literally blinding itself with its own waste heat.
Then we have the power constraint. Looking at the data breakdown of system efficiency, it reveals a huge bottleneck. To produce a laser output of just 100 kilowatts, the system demands an enormous electrical input of 300 to 500 kilowatts. That means a massive 200 to 400 kilowatts of energy instantly becomes waste heat. You have to remove that heat somehow, which requires giant generators, heavy liquid cooling loops, and incredibly complex thermal management systems. This is precisely why large Navy ships are currently the absolute ideal platforms for these weapons, while smaller mobile ground vehicles or aircraft really struggle to carry them.
Section 5. The Layered Defense Ecosystem. So, where does this leave us? Well, it paints a really clear picture. The laser is not some magic silver bullet replacement for every weapon on the battlefield. It is instead a highly pragmatic, specialized piece of a much larger defensive puzzle. Here, we're looking at two totally diverse environments: Israel's Iron Beam deployed on the ground against rocket swarms, and the U.S. Navy's Helios deployed out at sea. These environments prove that lasers act as an incredible force multiplier for close-range protection. They aren't replacing traditional systems, they're standing right beside them, taking out the cheap, close-range garbage so the really expensive missiles can be saved for the heavy hitters. To sum it all up, the reality of future warfare is a seamlessly layered air defense ecosystem. It's going to combine advanced early warning radar and AI tracking to classify targets. It'll use highly expensive, long-range kinetic missiles to obliterate heavily armored or distant threats. And then, forming that critical innermost shield, you'll have incredibly cheap, close-range, directed energy lasers sweeping the 0 to 10 kilometer zone. It is a holistic, multi-layered shield that fundamentally alters the entire arithmetic of modern conflict. Which leaves us with this final, incredibly profound strategic paradox to consider. How does warfare change when the cost of destroying an incoming threat drops to the price of a cup of coffee, literally solving the economic burden of defense overnight? Yet that exact same miracle weapon can be entirely defeated by a cloudy day?